Okay, Bismillahirrahmanirrahim. Any questions before we begin? Yeah.
How do you manage to gradient vectors? I mean, one in the x direction and one in the y direction into one matrix?
Okay, question. How do we merge two gradient values? So think about 1 pixel, right? So the question is, how do we merge two gradient values? There is one in the x direction and one in the y direction into a single matrix. So the first thing is that gradient is a vector at every pixel. So if you want the gradient vector, you don't need to merge them. The question is not how, I mean why.
One matrix such that it gives us the information that on every pixel there is a vector. Is there a way to?
A vector is not a single matrix, right?
But we want a matrix. I mean, for in the later part when we are.
Think about what you're saying. You want a matrix where at every pixel there is a vector. So that's not one matrix, that's two matrices. Or it's a tensor where every pixel, so you can either have, so let's say your image was 100 by 100 pixels. You can either write this as a 100 by 100 by 2 matrix, right? Which is no problem in MATLAB. MATLAB allows that to do. Or you get to write it as two separate 100 by 100 matrices. If you really wanted to come up with a combined information in the gradient vector as a single number, then you can either take gradient magnitude or you can take its direction depending on what you want to do. Or you can find the Laplacian of the image and that's a single scalar entity. But I don't think that was your question. I mean, say that.
I just wanted to a valid representation for us.
If you want to draw a picture like I did where I had gradient vectors on it, then that is actually using vector information, not scalar information, right? So MATLAB has a quiver plot which allows you to plot vectors at every pixel, but it is actually vector information, not scalar information. And gradient is a vector entity, right? You know that from your math. All right, any other questions? Okay, so where are we? Why don't you summarize? What were we doing last time or before that? We talked about panoramas, yes. Okay, KLT. So we discussed KLT, which is a feature. It's a local feature. It's a point feature. And I can use the neighborhood around, so I can use KLT to find interesting points which are corners in the images which have derivative in two directions, and I can use a window around it as a descriptor of that if I want to, so that I can match between two images. And you are trying that out in your homework also, right? Okay, so what else? What else were we discussing? Seam. Yeah, we discussed how if we have two images that we have warped onto the same coordinate system and we want to merge them together, what might be a strategy for that, and we discussed seam carving at one very elegant strategy for that, right? SIFT. So SIFT is, so essentially we were discussing feature detectors, and we discussed KLT as the first feature detector, which is based on the eigenvalues of the mean compensated covariance matrix, for zero mean data. Okay. Then we discuss, and we use that to build a panorama. I can use really any feature detector and matching strategy to build a panorama. Okay. So I showed the example of KLT. But then we said, okay, let's try a more complicated feature detector, which is SIFT. And we saw that SIFT has some very nice invariance properties. Invariance to scale, invariance to rotation, invariance to a lot of different types of lighting changes, and it can even handle a bit of projective distortions, even though it's theoretically not fully invariant to them. But because of the way the feature detector is built, it affords you certain invariances, and therefore it can match in very challenging data which has geometric and photometric distortions in it. Okay, when I say geometric distortions, I mean there are like stretches and projective distortions maybe, or affine distortions to the image. And when I say photometric distortions, that means there have been lighting changes, shadows, and things like those in the image. Okay. And as an example, I showed you the SFM example, the structure for motion example of Noah Snavely and others that we had discussed before. They were up against a very difficult matching strategy because they downloaded millions of images from the internet, from Flickr. So essentially they would have not been able to do anything if they don't have a matching strategy. And the matching strategy they used was actually that of SIFT as the first step in. It's an elaborate algorithm, but the first step of that is to apply SIFT to every frame. Okay, so it's a very, very powerful feature detector. But now I'm going to talk about, this is kind of maybe the last lecture in the series of talking about features, and we'll see how this propels us into classifiers. I'm going to talk about, in the very beginning I had said there are local features, there are regional features maybe, and there are global features. Okay, so I'm going to talk about non-local features. Features which are, so point descriptors like KLT or even SIFT, I would say they are local features because they try to detect a point of interest, an interesting point, or a corner, some place which has interesting gradients in the image. Okay, you know how they do that. KLT explicitly does that by looking for gradients which vary in more than one direction. They vary in two directions by rotating the covariance matrix, by rotating the data so that the covariance matrix becomes diagonal. Okay, SIFT does the same thing of finding interesting regions actually by applying a series of difference of Gaussian filters. The difference of Gaussian filter will give you a high response where there is kind of like a matching structure, a changing structure in the image, right? And so it kind of focuses on those parts of the image and builds a descriptor, builds an elaborate descriptor of that allows you to do very good matching. Okay, but both are kind of like local image features. And now let's talk a little bit about non-local features very quickly. Okay, I'm talking about these because they are a precursor to a lot of work in machine learning that is now part of computer vision, and then we will switch to the next module, which is that of machine learning. Yeah. Oops. Is that good? Okay. All right. So that's what I'm doing now. That's the story so far. Okay, of non-local features. Okay, so one of the very famous ones that I'm going to discuss, like SIFT, is a very famous local descriptor. Histogram of oriented gradients, or HoG, is a very useful descriptor for different types of structures that you might see in an image, which are not like point descriptor. It's not a point descriptor, but in many ways you will see that it's kind of like, I mean, I like to think about it as kind of like an extension of SIFT, and that's why I discuss SIFT. And again, you see how important the concept of gradient direction is in computer vision. It really is a surprise that the direction of gradient contains so much information that allows you to do useful stuff. Okay. By the way, there is a long history of feature descriptors or interest operators in computer vision. If we go back historically, we'll talk about a lot of different feature descriptors. But this is like, in a sense, the culmination of that work. SIFT and HoG, in my view, is very, very important for every computer vision student to know, even though there are some other ones that you should be aware of. Okay, so again, just to understand the importance of this research, this paper came out in 2005 by authors Dalal and Triggs. I just checked today, it has about 23,000 citations on Google Scholar. I told you anything above like 500 citations, you should look at that with respect. Anything above 1,000 read citations, you should read it. Maybe anything above like 5,000 citations, you might frame it and put it on your wall, right? So, I mean, these are like very, very important papers in computer vision that are being cited this many times. Okay, so what's the key idea here? Okay, as the name says, it's in fact, I could have given this name to SIFT also, right? Because SIFT also created a histogram of oriented gradients, Remember that in a 4x4 grid, first you decide where you want to make that grid by doing that difference of Gaussian filter all over to find an interesting location. And you also, from the scale of that filter, you decide how big you want to make that grid. But then you get 4x4 blocks. So there are 16 blocks, and in each of the blocks you make a histogram of oriented gradients. You make a histogram of gradient orientation. So the horizontal axis of the histogram is degrees, okay, and then in that you you put as many votes as the strength of the gradient magnitude for every orientation direction, except you normalize them to, you clip the votes to some very large value by doing a normalization, so that one cell doesn't overpower everybody else, and you have some detailed tricks like that in the paper, okay. But this approach is also kind of very similar, okay. But the purpose of HoG is not a local feature descriptor, unlike SIFT. Its purpose is actually not to aid in homography estimation or point-by-point image matching or fundamental matrix estimation. Those are the sort of things that you typically use a local operator for, okay, as you are doing in your homework, for example. This one is motivated by the object detection problem. The idea is I have a picture and I want to detect objects of interest, like persons, for example. Okay, so how do I do that? Now that's the first time we are talking about that sort of a problem, because that's an image recognition problem, and the rest of the course from now on is actually going to be talking about that problem only, which is the image. And in fact we are studying these descriptors as a motivation to the image recognition problem. Okay, so the original HoG paper was actually written to be focused on pedestrian detection in vehicles. You have a car driving, and you have a camera looking forward in the forward view, the sort of camera that is used for adaptive cruise control, for example. And now if there is a person crossing the street, the adaptive cruise control or the controller of the car should realize that. So that's a safety device, really. It should alert the driver that there is somebody crossing close by, and you should not Now, of course, now we do that by deep learning, and we'll look at how we do that. But this paper was the motivation. It was a pedestrian detection motivation. So these types of images, these are the types of results. Now, this is by no means an easy problem, because like I showed you in the very first lecture, cats come in all sorts of forms and colors and shapes and textures and deformations, right? That's also true for humans. I mean, humans come in all sorts of everyone is wearing different colored clothes here. There might be different lighting. There are different deformations that a human body can take. There are different camera viewpoints. So there's a lot of deformation that you can see in human body also, right? So it's not an easy problem. It's not an easy problem to isolate out of all the possible windows that I could have drawn in this image at different locations and different scales, to isolate these red ones automatically, that these actually correspond to a person. Okay. All right. So so this is the sort of data set they use now. Now this is a pretty diverse data set, except one of the things which is not as diverse about this data set is that the camera is not going to this view when looking at a human, right? It's always kind of like a horizontal view. The optical axis is roughly like parallel to the ground plane. Okay, so the person is seen as vertical. It's kind of like the view you would get from your eyes when you are walking on a street, the viewpoint that you would see of a person, or the viewpoint that you would see from your car if a person is crossing in front of the car. Okay, so that's kind of a restriction that they imposed on their data set, because that's the problem that motivated them. But other than that, they did not put any kind of specific restriction, types of clothes, types of lighting, types of environment, the background, pose, which way the person is pointed to. They did not impose all those restrictions. Okay, so it's a pretty realistic data set to work with. Now, the way the HoG descriptor works, and when you're thinking about it, keep contrasting in your mind with SIFT maybe, because SIFT is the local descriptor. So the way it works is that it works on a fixed window size, and that window size is 64 by 128 pixels. I mean 64 in width and 128 in height. Okay, and it's used in sliding window fashion over the image to compute this descriptor at all possible locations that I can do for this window size in the image. Okay, so I'm going to take a window of this size and I'm going to slide it all over my large image, and for each one of them I'm going to compute this descriptor. And if it turns out that that window is a person, then the descriptor will have kind of particular values, and if it's not a person, it will have some particular other values. Okay, now because persons themselves, because of perspective, can be of different sizes, what they do is they don't resize the window. They keep the window size fixed as 64 by 128, but what they do is whatever image you are given, they make multi-scale copies of that image. Okay, so that's kind of equivalent to like resizing the window and applying it on the image. All right, so that was their strategy. This is the paper in CVPR 2005. Yeah.
So what's the difference in resizing the image and resizing the filter? So we will get same results.
Yeah. So I'm saying it's almost equivalent. No, not exactly equivalent, but almost equivalent, and this is the strategy they use. So they have a fixed descriptor that they defined, and then they said I can apply it to images at different scales, so that I get some sort of scale invariance. Okay, notice that SIFT had a specific scale invariance strategy built into it, which was because of the derivative of the difference of Gaussian filter applied at different sigmas. KLT did not have a scale invariance strategy, so you could have used the same strategy for KLT, try it for different window sizes or different image scales, and this is what they did. Okay. Now, so what they do is essentially for that 64 by 128 window, they compute some sort of feature vector, some sort of long feature vector, and this feature vector is passed to a classifier which is trained to distinguish on this feature vector. It is trained to distinguish between images of persons versus images of anything else. Okay, basically they took a lot of images of pedestrians like these ones that I'm showing you, and a lot of images where they marked manually that they are not pedestrians, and then they computed this feature vector and had a classifier learn the difference between them. And the classifier they used is a very famous classifier. It's called support vector machine, so we'll talk about that. It's a linear discriminator. It can be a linear discriminator. So we'll talk about that in the next module in detail of how they did classification, or how generally classification is done in machine learning. So I'm not talking about that. I'm just focusing on the feature vector. But the assumption is that once you compute a good feature vector, that should allow you to distinguish between your object of interest and every other class. Okay, so that's the strategy. All right. So these are their steps. This is during training time. You are actually computing features of images that you know are persons. Okay, so you have an image like this where there is a person. I mean, this has already been isolated, so you know it's a person because you're going to put this into a classifier. Okay, so what they do is the first step here. I'm just skipping that. The first step here is normalize gamma and color. So this is sort of like a color normalization step. It's an image processing step that allows you to approximately normalize the range of colors in the image, because these images are coming from different cameras and so on. Okay.
So does normalizing mean converting it into grayscale?
Converting to grayscale is one type of normalization. Here they are doing some slightly different color normalization. Okay. We haven't talked about how color is generated in cameras and what's the difference between color generation of one camera versus the other. So I'm just skipping this step. Just assume that there is some sort of color normalization, like conversion to grayscale, for example. There's some sort of color normalization going on. In fact, they normalize color, and I think then they convert to grayscale before they move to the next step. Okay, so we can just skip that. It's not terribly important how you do that. Okay. And then the next thing they did is compute gradients. Now you know all about that. The mask that it uses is -101, which is awfully similar to the one we use, which is -1 and 1. A lot of people use this mask rather than just -1 and 1, because -1 and 1 is not a symmetric mask in the sense that the origin of the mask, if you place the origin as +1, then it is disbalanced on one side in terms of its span. And if you place the origin on -1, then it's disbalanced on the other side in terms of its span. So just to keep it symmetric in terms of the number of pixels that contribute to the result at a particular location, is symmetric about origin. They sometimes use a mask like this. It's actually quite popular. And it gives you, remember when we talked about gradients, we said a larger mask might give me more gradients because it's differencing over a larger area, where I should use smoothly varying gradient with noise. So it's kind of like the idea that this mask is quite popular. But the net effect of this mask is quite similar to the mask that you have used. In fact, I think in their paper they did not recommend using any smoothing, which is a bit odd. Okay. People have different types of smoothing strategies, and we discussed one of them. Something that we have found quite effective is what we typically do is when we are doing gradient in this direction, like this mask in the horizontal direction, we actually smooth in the vertical direction so that my horizontal derivative is not impacted by vertical changes between one line and another. And then when we apply the mask in the vertical direction, we often smooth in the horizontal direction. That's a strategy that we have found to work quite well. But anyways, they did not, I think, apply any smoothing, and they said it seems to work well just without any smoothing for us. Okay. So they computed some gradients, and then what they did was, because you have gradients, you can compute the histogram of those orientations of gradients pretty much like SIFT. Okay. So what they recommend in their, so this is again a weighted voting strategy. You'll build a histogram on angles, but the amount of votes that you put in every angle is proportional to the gradient magnitude there. So if you have a strong gradient magnitude, you will put more votes for that angle. So let's say the angle was 45 degrees at that location, you'll put more votes for 45 degrees if there was a very strong gradient, and if you will put less votes for 45 degrees if it was a very weak gradient in terms of its magnitude. Okay. So they suggested using 9 bins. Now SIFT used 8 bins. They use 9 bins, again divided by 45 degrees, but 0 and 180 are kind of repeated there, I think. I'm not sure if 0 and 180 are repeated, or they're just uniformly distributed on 9 bins. They seem to suggest, because their objective was in the end was a classifier, what they did was they built a classifier, and then these are parameters going into the classifier in a way, how many bins to use, what type of normalization to use, and so on, what type of gradient mask to use. And they, in their paper, they experimented with a lot of options, and they said these are the options we have selected, which for our problem gave us good results of the classifier. So the objective was set to be good classification accuracy. But this doesn't really terribly change the results in the sense of whether I use 9 bins or 8 bins. It's approximately the same. It's the crux of the idea which is the matter here. Okay. So what I do is I use 9 bins divided in 0 to 180 degrees, and then we say unsigned angles because a gradient direction of let's say 45 degrees is the same gradient direction as 215 degrees, but that's just going opposite. Okay, so they used angles only between 0 and 180 degrees. Whatever was more than 180 degrees, they subtracted 180 from that to map to the same orientation. Okay, and then they make these histograms in k by k pixel cells. What is k by k? That depends on how many boxes they're going to fit in that 64 by 128 window. We'll talk about that. Okay, and then so here this is not a very clear picture, but I get these histograms at a lot of locations. Okay, and these are basically orientation histograms, so they are being shown by the length of the vectors in the histogram bins. Okay, and as usual, the votes are weighted by magnitude. Okay, so then they do one other quite interesting step. Remember, SIFT also had some sort of normalization step, so that lighting changes don't matter much and so on. So they did. They didn't. These guys, because they are computing a lot of these HoG blocks, they did not compute. They did not specifically compute normalization of just one block independently. Okay, There is this debate about local normalization versus global normalization. Think about it. If I have a large area and I make small blocks out of it, okay? Now one of those blocks lay on that wall where there aren't many gradients at all, okay? But I say I'm going to normalize those gradients, I'm going to make the magnitude of that vector 1, okay? Then that really means that even those very noisy gradients will get very enhanced in my normalization, because those values were all close to 0. I divided by the magnitude, they're going to be enhanced, okay? So there is a case to not do completely local normalization, because then some very noisy things which are not very relevant to your image will get enhanced, okay? So maybe I should just compute all those small blocks and normalize once globally, okay? That would be a more fair strategy, maybe. But then we know that there are portions local in the image which are interesting, and maybe there is some interesting feature here, but in global normalization it's too weak to stand up because there was some very strong feature here. So this strong feature in its normalization is going to snub everything else, okay? If you have a long vector and there's like a big value here, all those values were between 0 and 1, and then there's one big value which is 100, and then I normalize the whole vector together, this 100 is going to make everything else approximately 0, right? So there's a case for local normalization, so that some one global feature doesn't overpower everything. But there is a case for global normalization, because local normalization can even enhance some very noisy and very weak features which should not be enhanced. So they actually took a very interesting strategy of semi-local normalization. What they did was, when they are computing these hogs in different blocks, okay, so they normalize over adjacent blocks. So they actually do, for a 3 by 3 set of blocks, they actually do 4 normalizations, okay? What they do is they normalize these 4 together by 1 scale factor. If I'm computing the feature vector at this center block, okay, so I'll compute this center block normalization with these 4, okay, normalize that to 1, then I compute normalization with these 4, then I compute normalization with these 4, and then I compute normalization with with these 4, okay? So every point at which I'm computing hog, I do 4 different normalizations of that point. One with these neighbors, one with those neighbors, one with those neighbors, one with those neighbors. So I get to normalize it in a semi-local way. And I normalize it with just the L2 norm, except if the L2 norm is too close to 0, the value would increase too much, right? And so they have, in the denominator, they have a small epsilon factor, which prevents the denominator from ever coming very, very close to 0. Okay, so that's like a snubbing factor of not enhancing noise too much. Okay, it's kind of like a regularization term there. Yes, yes. So I'm computing a vector at the center yellow location that is marked here, which is the hog vector at that location, but there will be 4 copies of this vector. One normalized by these neighbors, one normalized with that neighbor, and so on. No, I'll use all 4 of them as my features. Yes. Sorry? Yeah, I mean, assume there are no Gardner cells. That's not terribly important. I mean, whatever region I compute it with, for every one of them, I'll compute with 4 neighbors. Okay, so assume that the last ones are ignored. I don't compute there. Remember that I'm computing this feature for a window embedded in a large image, so I can always spill over and compute those and then just keep this result. Okay. All right, so what's the size of the feature vector here? Okay, what they do is they do in their 64 by 128 window, they make 7 by 15 cells. Okay, that's their strategy, because they said we'll keep a fixed size and we'll just rescale the image if we want to apply it at different scales. Okay, so they have 7 by 15 cells. So their number of features are 7 by 15 because that's the number of cells, multiply by 9 because every histogram has 9 values in it, right? Because that's the length of the histogram. But then there are 4 copies of it. Because that histogram is normalized 4 different times for each cell. Okay, so it becomes a pretty long feature vector, 3780 length of the vector. So every window that I make, like this window in the image, every window that I make, I can compute a 3780 length feature vector for it. Okay, is that number clear? How did that come? It just comes from their choice of parameters here. 15 by 7, which is the number of cells, and then 9 orientations for each cell, and then 4 normalizations for each cell. Yes. 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 So that's the length of one histogram, one orientation histogram. In SIFT, that length was 8. Here they somehow chose 9. And they justified it in the paper by saying, we tried a lot of different numbers and this gave us a little bit better results. So it's just empirical observation for their data set. I mean, if you're doing it, you might just pick 8 or 16 or some other number if you want to. But I'm just describing the way it's described in their paper. Okay? All right. So this is what happens. You have an original image, like this particular sub window of an image, and you compute the HoG features for that, and this is what the HoG features might look like. Okay, the HoG features would favor orientation, so this is where the legs of the person are, because there are more vertical orientations at that location, right? And here is a floor, so that's more horizontal orientations and so on. Okay, I haven't talked about SVMs, so I'm not talking about how classifiers work, but essentially, just to give you a preview, because you will compute this HoG features for all the example images that you have of actual positive class, which is persons here, and you will also compute it for all a set of images that you have which are just negative class, which is images like this, but they don't have persons. It's just images of background or so on. They don't have persons in them. Okay, and your classifier actually is a strategy which learns the difference between them. It learns what distinguishes on this feature vector that I'm feeding it. I'm not feeding it images. I'm only feeding it this feature vector. Okay, but I say this 10,000 set of feature vectors is actually what persons. These are feature vectors of persons, and this 10,000 set of feature vectors are feature vectors of non-persons. Okay, and then I say, all right, the classifier is a strategy which learns the difference between them, which learns the distinguishing characteristics between them. Okay, we'll talk about that extensively in the future lectures, inshallah. But here we are visualizing actually what the classifier distinguished as portions of that feature vector which distinguish between those two classes. Okay, and it's instructive to see, because you see kind of like in the histogram representation, you kind of see like an outline of a person. Okay, the classifier learned that these are the types of gradients. If gradients take this form, that's actually much likely to be a person than to be a non-person. That's what the classifier distinguished. Okay, and so this figure really, you should view this as the strength of the gradient orientation feature, because the gradient orientation feature, if selected properly, or the proper components out of the gradient orientation feature, can actually describe an object for you. Okay, essentially, in a way, what the classifier learned is that if my sub window contains a person, then at the top I should see gradient orientations like this, and then I should see gradient orientations like this, and then the gradient orientations for the leg and so on. If those are the types of gradient orientations that I see, it's actually a person. So it's actually showing you the strength of what a gradient orientation feature means. All right? Okay, so here I'm just showing you this. Somebody made this visualization. I gave you the link there. Here I'm showing you, this is the original image. It's a Jeep with, I mean, in an exhibition, and these are all the HoG histograms for that. I mean, this is not done in a 15:7 window. This is done just in small blocks all over the image, just to show you that the orientation of, I mean, the gradient orientation histograms actually encode a lot of information for you. Okay, notice where you have plain areas like this door, you kind of have like a lot of orientations available, but then the bottom of this door is strongly oriented in this direction, and you can actually make out the outline of the door or the hood, right? They're all pointed in that direction, diagonal direction. The middle of the wheel is kind of like all directions, but if you traverse the sides of the wheel, you can actually just moving in the dominant directions here that you see in the histogram, you can trace the whole wheel. Okay, so it is a descriptor of the content of the image, and that's why SVM worked very well on it, because this was like just like cooked for the SVM, so that the SVM can learn the distinguishing characteristic of the class that I'm trying to learn.
This is the result after SVM?
No. This is the raw HoG result, and it's not exactly HoG also, it's just the orientation histograms. It's a visualization of the orientation histogram. HoG does this in Windows, and it has a specific size and so on. Okay, but I'm just showing you to give you an understanding of why the orientation histogram is so important. Okay, so here's a visualization. This is a video. In every frame of this video, in all possible windows in that frame, they are computing HoG and then classifying, giving that to the SVM to say whether that window looks like a person or not. And so remember how much computation is being done here. Video is a lot of frames. Okay, in every frame I have to try all possible locations of this green window that I can get. But it's not just that I'm trying all possible locations in translation, I'm also resizing the image, because remember, the person here at this end is actually awfully smaller compared to the person here at this end, right? So I have to, because HoG is a fixed size feature, I have to resize on multiple scales and keep trying. So for every frame, I'm resizing it to multiple scales, trying all possible translations in it, okay? And then giving that to an SVM to classify, computing the HoG feature for that, and then giving that to an SVM to classify. And then I did that for all frames. I didn't do it. I mean, this guy Sulman Beg did it. Okay, so all power to him. But this is what the results look like. It is actually a pretty good result. You see, yeah, sometimes you miss people, so there is some flicker in these boxes and so on. But yeah, you have occluded people, right? When this person passes, you have this. I mean, you only see half the lady here because she's the legs are being occluded by this stroller. You have people wearing overcoats, people wearing different clothes, colors, stroller, group, right? I mean, it's actually. Don't think it's a simple result. Yeah, I can see a person there, yes, but for the computer to figure out that these are all people is actually pretty hard, and to distinguish that from all possible image blocks that were not people. Yeah, I don't know. Yeah. I don't think this is happening in real time. Even though there are implementations of HoG that could, given enough hardware, I guess you could implement it in real time. But this is not a terribly fast process, yeah. You could, if you have good hardware in your surveillance cameras. There are some pretty powerful cameras out there now with very strong either DSP or FPGA architecture with them. Okay. So yeah, it could be implemented in real time. It's a matter of hardware has grown very much, so it's a matter of putting enough hardware there. But I'm just giving you the order of magnitude of computation here, of how much computation I have to do to be able to get a result like this. But these days we can do that in real time, so it's not a problem. In fact, when we talk about deep networks, they are doing maybe more computation than this. Or another way to say that is that HoG can be implemented in a neural network also by choosing specific weights. We'll see that maybe when we when we talk about neural networks. And there are some very, very optimized architectures that are coming out these days. It's very exciting times for deep learning. So there are some very optimized architectures that are coming out for deep learning. And so if you can map a problem to a neural network type of architecture, you can actually get very fast hardware for that for quite cheap. So just as an example, typically we use GPUs by NVIDIA. NVIDIA is the leader in this industry now, but there's a company that Intel just recently acquired, Moverius, and they have come up with a neural compute stick, which is only $80, and it's like a USB drive, but it's actually an architecture built with a USB interface. It's an architecture built to optimize deep learning computations. So you can just stick it in your computer and run a pretty decent neural network on it, doing something like pedestrian detection, only for $80. And you can stick it to a Raspberry Pi and embed that with a camera if you want to. All right. Okay. So yeah, question. Yeah, this is for one window. So this is 15 by 7, I think. 1, 2, 3, 4, 5, 6, 7. Yeah. Yes. So this is for one window because I'm showing you how the descriptor is built. Now, when I'm given a real image, I will try all possible windows on it. Yeah. Okay, so just a summary of our HoG features. HoG features are pretty suitable for learning the overall shape of an object. It's kind of like a descriptor to describe an object. If I were to ask you, in English only, write a description of a human, okay? So that, write an essay for me in words, in English words, which describes a human, so that it's applicable. I can use it as a feature. It's applicable for all humans, and it's not applicable for anything other than a human. Now that would be a pretty hard thing to do, right? So that's the problem that HoG has solved for you. I mean, I'm just giving you kind of a visualization of why is HoG important. That's the problem HoG has solved for you. HoG has said, the description of a human that I'm going to use is this oriented gradient histogram, okay? And it turns out that it's a very suitable description if you wanted to learn what is a human versus what is not a human, okay? And that's our topic for the next module. The rest of the course, we'll talk about that learning problem. Okay, and they describe the spatial distribution of image gradients of a shape. Why do I say that? I mean, it's not just one image gradient for the whole thing, one gradient histogram. By putting a grid, you actually have the ability now to learn the difference in gradient of this part versus this part, right? Because you have divided it into a spatial grid. So that's why I said a human is like on the top, the gradients are like this, and at the bottom, the gradients are like this. That's what a human is. That's essentially what HoG is. So HoG is learning a spatial distribution of the orientation histogram of image gradients. Okay. Given a lot of examples of a particular object, for example, pedestrians, we can learn the similarity between their HoG features, and then this is really, I'm giving this you as an example of a regional feature or maybe a global feature if you compute it for the whole image. And these types of features are used in object detection. Okay, you find appropriate features and train a classifier. This has been actually the strategy for machine learning and computer vision for last 20 years till 2012, where we actually gave up on this strategy when deep learning came out. So we'll contrast this to deep learning. Because in deep learning we don't learn features, but before that, and in some problems even now, people look for appropriate features so that the classifier has an easy task to do. Okay. All right. Any questions? Yeah.
So in that particular video, there were also mannequins, right?
Yeah.
So was that video taking 2 frames and seeing if the object has moved and then classifying?
No, not really.
How did it?
That's a good question. I could have used motion to say humans typically move, and so I will only find those pedestrians which are moving between the images. In fact, Dalal and Triggs wrote a paper next year in, I think, CVPR 2006, where they used that strategy to filter some of the wrong matches which they were getting. by looking for motion, because they were looking for pedestrians on the road, and on the road pedestrians would typically be moving. But that's a risky strategy depending on what your application is. What if a guy comes in the middle of the road and stops? Is your algorithm gonna filter that out, that that's not a valid person? And so like, you can hit stationary humans but not moving humans. I mean, is that going to be your strategy? This has become a big issue in these corner cases, right? Sort of outlier cases have become a big issue in self-driving cars, because self-driving cars train on lots of data. But if there are scenarios that don't exist in that data, like maybe construction sites, there are very few examples of construction sites in your data set, then you are unsure how your vehicle is going to come and behave close to a construction site. Okay. This is, by the way, we'll talk about these issues when we come to learning. Humans are pretty good at that in generalizing from a few examples. And even if they don't see an exact same example, but they still are able to make some inferences. This is example from raising my kids. My son, when he was young, I mean, he learned what is a horse by looking at a picture of a horse and seeing a horse, and he learned what is a donkey by looking at a picture of a donkey. And then somewhere when we were driving, we saw a mule, khachar, which is somewhere in the middle of a horse and a donkey. And when he saw that for the first time, he couldn't figure out whether it's a large donkey or a small horse. It's kind of like weird, right? But that generalization ability is possible. You have actually locked it to a class somewhere between a horse and a donkey, where it varies in the size between them, right? That's a generalization ability that is very important in machine learning. All right. I want to talk about one last type of features, and in fact, this topic could have been in this module or next module. I could introduce this as a machine learning technique, or I could introduce it as a type of a feature. This topic is kind of in the middle of both. Okay, but it's fundamentally very important because it will allow us to interpret some of the things that we will do later in a different light. Okay, all right. So now we are going back to linear algebra, some very basic linear algebra, and I'm going to revise some things. You already know all of this, but I'm just going to emphasize certain things here. Okay, what we typically do when we talk about feature vectors is that we are treating an image as a vector, right? So that's done by a linearization of the image into a vector. So I took the first column, put the second column underneath it, put the third column underneath it, and put the fourth column underneath it, and I said this is a vector. Okay, so I can talk about any image as a vector like this. Okay, and you know that vectors, as soon as I define a vector, it's actually defined on some basis. A vector does not exist without its basis. Okay, so for example, when I say this is a vector AB, essentially what I'm saying is it's A times the horizontal basis and B times the vertical basis. So actually, when I define you a vector, but I don't define its basis, it's actually the identity basis, which is 1, 0, and 0, 1 in this case. Okay, so essentially what I'm saying is that I have two basis vectors here. Even if I didn't talk about them, you will assume that they were there. There's an x basis vector, which is 1, 0, and a y basis vector, which is 0, 1, right? And then when I said I have a vector AB, what I essentially mean is that AB is really a scalar A times the first basis and a scalar B times the second basis. Okay, that's the notion of basis vectors. It's obvious you are familiar with that. So any vector can be written as a linear combination of basis vectors. Agreed? We have done this before. Now, so what's a vector basis formally? It's a set of vectors V1 to Vk. They form a basis in some vector space W if, well, V1 to Vk should be linearly independent. You understand what is linear independence? None out of those can be written in the form of any previous one, a linear combination of the rest. Okay, and then they should also have the capacity to span W. There should be no vector in W that is not reachable by a linear combination of V1 to Vk. If those two things are true, then it's a vector basis. Okay, and the identity matrix is taken to be the standard basis in whatever vector space you are working with by default. Okay, so all vectors if V1 to Vk are a basis, then all vectors in a vector space can be expressed as a linear combination of V1 to Vk. That we really say that V1 to Vk span the space, because every point in the space is reachable by a linear combination of V1 to Vk. Here's an example of identity basis 2, 2, 2 can be written as 2 times this and this and this, or I could have a different basis for this space. These 3 vectors are a different basis. They are not identity, but then this same point 2, 2, 2 is still reachable as a linear combination of them. Agreed? Just I've given some definitions here. Formally, a vector space is a set of vectors which is closed under addition and multiplication by real numbers, and a subspace of that vector space. That's another concept we have talked about before. In fact, you have implemented in your homework, right? When you implemented points on a plane in 3D, they were 3D points, but they lay on a plane. That's actually a subspace. It's a 2-dimensional space of a 3-dimensional space. It's a 2-dimensional subspace of a 3-dimensional space when all the points were on a plane. Remember, when you generated points on a plane, they were actually 3 vectors. They were not 2-dimensional vectors. They were 3-dimensional vectors, right? Every vector was a 3-dimensional point, but they were restricted to lie on a plane. So that was the subspace. Okay. All right. So one fundamental operation that I can do is I can represent my vector. It's represented, let's say, on an identity basis or on some basis, and I can change its basis. There's an operation of change of basis that I can perform. Okay. So what's the idea here? I have this vector AB. So instead of the bases, identity basis, which is x and y here, let me define 2 more bases. This is a new basis which is actually rotated 45 degrees. Okay. So the new basis vectors are, this vector is 1 over square root of 2, 1 over square root of 2. I could have written it 1, 1, but I normalized it to unit length. So it's 1 over square root of 2, 1 over square root of 2. And this one is minus 1 over square root of 2, 1 over square root of 2. Okay. It's still an orthogonal basis. Okay. Now, if I want to take a particular point, let's say the same point AB, and I want to represent it on the new basis, how will I do that? AB is the representation of that point on the identity basis. Now I want to represent it on this basis. How would I do that? I will take the dot product because I really want to know what's the projection of this point onto those bases. Okay, so this is the x value now, the new x value, and how, I mean, this length would be the new x value for that point, and how will I compute that? And this would be the new y value, right? The projection in that. And how will I compute that? I will compute A prime, which is the new value here, as just the dot product of AB in the original basis with the new basis vector, and B prime will be the dot product of this with the new basis vector. Okay, so the dot product gives me the length of the projection here, and so that's just a way to perform the change of basis. All right. Notice that it simplifies because I normalized the new basis to unit length. Otherwise, I would have to have some scale factor there. Okay, so which makes, if I want to write these 2 operations as a single operation, I can write this. This really is the same 2 equations. Agreed? And now realize that since AB is a vector, I had to actually take the transpose of my basis matrix. I mean, this is really the transpose because that's the x basis and that's the y basis, because that's how the dot product would work. All right. So with a matrix multiplication, by the transpose of your new basis, you can just perform a change of basis. That's the lesson here. Agreed? Very, very simple and straightforward. All right. One last comment about this background is that the bases do not have to be orthonormal. There's no condition on that. The bases could actually be non-orthonormal as long as they span the space. These 2 vectors, which are drawn in red, they still span this space, the space which is a plane, okay, R2 space. They still span this space, which means every point in this space is actually reachable by a linear combination of these 2 vectors. However, if I am given a basis, a valid basis which is not orthogonal, if I want to, if I prefer orthogonal basis, I can always orthogonalize it. Okay, that process has a long name. It's called Gram-Schmidt orthogonalization. But it's actually really very simple. I mean, the name is more complicated than the process itself, right? The process is really this. I would take this A and B, I mean this V1 and V2, and I'll take their cross product. And the cross product will come out of the plane. And then I'll take the cross product of that result out of the plane, the normal vector, and V2, let's say, and that will give me a new V1, which will be orthogonal to the original V2. Agreed? So just by a series of cross products, I can always orthogonalize my bases if I want to, and of course I can always normalize them. So I can, if you give me a basis which is not orthogonal and not normal, I can convert it into an orthonormal basis if I want to, and it will be spanning the same space. Agreed? Okay, that's a bit of background. So why am I talking about this? Okay, it turns out that so these are linear basis changes, right? I mean, some other linear basis than the identity basis to describe my image vector. Notice that I can just take my image pixel values, write them as a vector, a long vector, and then that means that that vector is defined on an identity basis. Because I didn't specify the basis, by default that vector has identity basis. But I'm saying I can change the basis of that vector. Now the question is why? Why am I talking about that? And it actually turns out by an appropriate change of basis, you can form a feature which is very useful. Okay, so why do linear bases often give a compact representation of a signal? I want to illustrate that just by showing you this time varying signal. Okay, so think of it as a video, as a one-dimensional video which has 30 pixels in it. Okay, so this video is changing, or you could think of it as rows of an image, whatever you want to think about it. I'm giving you a one-dimensional example which changes over time. Now, at any given time, if I pause this, these are uniformly distributed random numbers actually. There are 30 uniformly distributed random numbers. Well, not uniform, maybe normally distributed, I don't know. I use some random number generator to actually generate them. Okay, so there is no relationship. If I tell you the first value, there is really no relationship of you telling me the second possible value for it. Okay, these are like really random. Okay, now if that is the case, this signal, whatever I write it as a vector, a 30-dimensional vector at any given time, that 30-dimensional vector is kind of a compact representation of the signal. I can't really make it any more compact because these numbers are really random. Agreed? I mean, if I want to represent them by lesser numbers, so in a more nicer way, that's going to be hard because these are random numbers which are not correlated between one and another. Okay. However, let me show you another signal. This is also, by the way, a random signal. You will see some randomness in it, but that randomness is not the same as previous signal. Okay, so this is how this signal varies. Okay, all right. Now, what's the difference between this signal and the previous one? It has some yani structure to it. There are 3 different levels at all times. So in a sense, one way to say that is that the first 10 points have some correlation in them, even though there is some noise. But if I tell you, let's say the value at any given time, I pause this, okay, and you knew what the signal was like, but you actually can't see the whole signal. I mean, you knew the form of the signal, like you had some idea about the form of the signal, but I didn't tell you what exact numbers do I have right now. I hid that from you. But I told you the first number is -10. You would get a pretty good guess that the next number is going to be very close to -10, and the next also, and the next also, all the way to the 10th number. They're all going to be very close to -10. Okay, and then I told you the 11th number is -5, and you will say, okay, so if you wanted to ask, if you wanted to learn quickly in very few questions what the signal approximately looks like, you will ask me, tell me any one of the first 10 numbers. Okay, so tell me the first one, tell me the 11th one, and tell me the 21st one. So you will just ask me 3 questions instead of 30, which you would have to ask for the previous one. Because in the previous one, if you ask me 3 questions, well, you only know 3 values of the signal out of 30. You don't know anything about the rest of the 27. That's what we mean by correlation between values, right? But in this case, if you tell me, you will ask me if you are intelligent, right? Assuming that you are, you will ask me number 1, number 11, and number 21. Just tell me those. And you'll say, I don't need to ask you any further questions. I know about about with 95% accuracy, because there's some unknown variation still, but about 95% accuracy I can tell you the whole signal. In fact, I'll write the signal for you, and the error between that signal, the least square error, the L2 norm between that signal and the original one will be less than 5%. Agreed? So this signal has a compact representation. And in fact, the way to write that compact representation is that I can have a 3-dimensional subspace of the original 30-dimensional space in which I represent the signal. I can have a 3-dimensional subspace spanned by these 3 vectors as bases, and then the signal at any given time is a linear combination of them. Agreed? It's the signal at any given time is something like C1 times the first vector plus C2 times the second vector by C3 times the third vector. Well, this is not an exact equality here, because there was some noise left over, but it's actually approximately equal. It's pretty close to equal. And so this is an example of, out of your 30-dimensional space, this signal always resides in a compact 3-dimensional subspace. Agreed? So instead of representing it as 30 numbers, I can represent it as 3 numbers. And that would be a compact representation of the signal. So if there is some regularity, I'm using this term regularity as an opposite for randomness. If there is some regularity to a signal, it can be exploited for a compact representation. And it turns out that, why would I want a compact representation? It turns out that compact representations give you better classifiers generally speaking. If you can find the right compact representation for your signal, you can actually get a better classifier at all. Now this statement I'm making very loosely, because we'll see lots of examples about this statement later, but I'm saying, roughly speaking, that's the reason why we are interested in compact representations of signals. Yeah. The lesser the dimensionality of the compact subspace in which the signal lies, I can generally get better classification. Not always, but generally. Okay. So for example, now coming back to real images, for example, there is a transform in those who study signal processing, there is a transform called the discrete cosine transform. It's really a change of bases from the identity bases to cosine vectors. Okay. This is what the bases look like for this transform. This is the first basis, which is really a DC value flat signal. This is the second basis, which is a really slow varying cosine. It's 1 wavelength of a cosine. The third basis, which is like 1.5 wavelength of a cosine. Fourth basis, which is 2 wavelength of a cosine, and so on. Every time you keep increasing half a wavelength. Okay. You can prove this yourself if you want to, or you can generate these cosine bases in MATLAB and try to take their dot product. They do form they do form an orthogonal basis. Each of these vectors is orthogonal to each other. Okay. So if I have an n by n image, how many basis vectors will I need to completely represent this image in a new vector space? So my image size is n by n, say 100 by 100. So what's the length of my vector? 10,000. 10,000, right? What's the length of one of the basis vectors out of the identity basis? Okay, let's go back. I have a 3-dimensional space. So what's the length of my identity vector? 3. And if I write out the whole basis, that will be a 3 by 3 matrix. So that's it. You always use, because you can't see beyond 3 dimensions very easily, you always use the analogy of 2 or 3 dimensions when talking about high dimensional spaces. So in this case, your vector space is 10,000 dimensional, because an image is 100 by 100 pixels, or really in general n square pixels. So your vector is n square by 1, and so your basis vectors is, each of your basis vectors is also n square by 1. Right? Which means you have an identity. If you wanted to represent the identity matrix, that's a 10,000 by 10,000 matrix of identity. Agreed? Yeah? Just by analogy to, there's nothing new that I'm doing here. It's just elementary linear algebra from the notion of bases. I'm just doing that very simple thing that I showed you in a very high dimensional space. Okay? So to completely represent this vector in a new vector space, what would be the size of each vector? Well, each basis vector would be again n square by 1, 10,000 square by 1, oh sorry, 100 square by 1, which is 10,000 by 1. If I write all of those bases, there will be 10,000 of those. So it's a 10,000 by 10,000 matrix of all basis vectors. And that new basis, the transpose of that, I will multiply by my image vector, and I'll get the new representation of my vector, which are really DCT coefficients. Okay. So just to give you a concrete example, so let's say this is my image. When I vectorize the image, I got this. It's a small example, and in fact, this is random. Okay, but this is my vector. So what I'll do is I'll compute because this is 8-dimensional, the DCT bases, if I arrange them, they will be 8 by 8 matrix, because there are 8 of those basis vectors, each one of them of 8 dimensions. So they will be 8 by 8 matrix, pretty much like the identity basis will also be an 8 by 8 matrix. So that's just a new basis. And what do I have to do if I want to convert this? I have to take the dot product of this vector with each of those bases, which can be done by really transposing this matrix and multiplying it just once. So it's one single matrix multiplication, exactly the same as I did in 2 dimensions for you. I'm just doing it in 8 dimensions here. For a 100 by 100 image, I'll do this in 10,000 dimensions for you. Okay, and so I can get a new representation for my basis vectors. In this case, if I do it, this is what it comes out to be for the DCT basis, the cosine basis that I showed you. Okay, and since I chose an orthonormal basis, DCT is an orthonormal basis. So since I chose an orthonormal basis, the actual magnitude of the vector does not change. So if I find the magnitude of this vector or I find the magnitude of this vector, it turns out that they're same, because orthonormal bases really are a rotation of the axis and nothing more, because orthonormal matrices are rotations. Okay, rotations or reflections. So it's really a rotation or a reflection of the axis. So it doesn't really elongate any of the vectors. It just rotates your data. Okay. All right. So here's the question: why should I change bases? I told you I can change bases if I want to. Okay. But why should I change bases? And I motivate that by the randomly changing vector that I showed you. It can turn out that certain bases may represent my data, my image, more compactly than certain other bases. Okay. For example, in a 3 space, if all my data lies on a plane, let's say this was my data. This data is randomly distributed, but it's random numbers oriented along a plane. You have actually generated data like this before in your homework. So you know what this data looks like. It's all points on a plane. Okay. So if that was the case, if I choose a basis which is aligned with this plane, okay, like a basis like this, so this vector and this vector actually span that plane, and this third vector is actually out of the plane, then this third vector will not have any energy on it. The coefficients along this third vector will all be 0, because the data lay along the plane. And so I can represent this data as 2 vectors rather than 3 vectors, as coefficients on these 2 vectors rather than on all 3 vectors, if I choose appropriately oriented basis. That wouldn't be possible. This is actually the same as what you did if you use that trick of using that M transpose, the null space of the plane, using that M to generate points out of only 2D points, converting 2D points into 3D points. Okay, so that 2 representation of that 3 vector was actually, I'm doing the opposite of that. I'm saying I can find the basis which will allow me to represent this data only in 2 dimensions. Is that okay? Do I need to repeat this? Okay, I'm saying if my data has certain structure to it, certain regularity on it, like in this case, the data lying in some subspace of the full space, then choosing a basis that span that subspace orthogonally is actually a more compact representation of my data. This is a very key point. So make sure that you understand this properly.
So you played origins and data first,
Yeah, assume that it's actually on the origin. The vectors actually are always drawn with their base at the origin, but I need vectors that span the data set. So assume this is a slightly not a nice figure. Assume that this data is passing through the origin, because we'll later also be talking about zero mean data. Okay, so assume that the point cloud is planar, but it passes through the origin. Okay, that would be a easier representation to what I'm saying. Not necessarily, but let's say we assume that it always passes through the origin.
So why not just
Yeah, that's true. That's true, actually. That's a good point. So subspace will necessarily pass through everything, yes. The ones that I've drawn, the ones which are aligned with so the bases have to be vectors on that plane for me to get compaction if the subspace was the plane. Okay. Sorry. Because the data is on a plane, so if I choose a vector on one vector on the plane like this and another vector on the plane like this, then I can represent every point as a linear combination of just these two vectors. Which is actually, you have done that before. You generated data like this, so you did it by construction. Here we are saying, okay, I can estimate those bases maybe, or I can change a basis so that I get those types of bases. Okay, this is actually the key idea behind JPEG compression. Which is something you use very frequently, right? So how does JPEG compression work? In JPEG compression, we divide the image into 8x8 non-overlapping blocks, like 8x8 blocks, and actually we compute the DCT bases, the DCT representation of each block, which means we transform the vector of that 8x8 block, which is 64 values. We transform those from the original pixel value vector, which is based on identity basis, to the DCT basis. Okay, so we represent those 64 values on a DCT basis, and so that becomes a DCT representation of that block. Okay, DCT coefficient. So this is the original picture matrix. These are original values. When I compute DCT, I get values like this. It turns out that for most natural images, images which are not synthetically constructed to be random, for most natural images like photographs you take, DCT gives us good compaction in the sense that the first few DCT coefficients have high values and the rest are close to zero. Like you see here in this matrix, the first values are higher here on the top left of this matrix, and then there are a bunch of zero or very close to zero values. Okay, so we say our images, our natural images, have some structure to them. They lie in the vector space, in the 64-dimensional vector space. They don't lie everywhere. They lie in some compact subspace of that, and that compactness can be exploited by DCT. This happens for really all natural images. One of the reasons why this happens for all natural images is that people have shown very robustly that natural images do not have a lot of edges in them. They have edges, but the portion of the image which does not have strong edges is more in general than the portion of image which does not have edges. Think about this room. I mean, a lot of this wall, the middle parts of the roof, maybe this carpet. I mean, there are a lot of planar areas in this wall, in this room, which do not have edges. If I were just to collect how many edges, how many portion of the view that I see is edges and how many I don't have, actually it turns out people have done that for very large data sets, and that forms a Laplacian distribution around zero. So the zero gradient places are a lot more frequent than the non-zero gradients. Okay, and that's what DCT is exploiting. So DCT is saying, I will find a few regions which are slowly varying. I will find a lot of regions which are slowly varying. The first basic vector was flat, which is like this wall. The second was very slowly varying. The third was a bit faster. But I won't find a lot of energy, a lot of types in the image which are very, very fast varying. I can have a few places, but not a whole lot. Okay, and that's a universal property of natural images, and that's why JPEG works so well on all types of images that you have. Okay, so what we do is we ignore the small coefficients which are close to zero. We save only the large ones, and that's the image that we encode and transmit. It's a lot less values than the total pixel values in the image. Okay, and now we can reconstruct, because I did a change of basis. I can do the inverse of that change of basis, and I'll reconstruct on the other side. Okay, these are DCT basis vectors. I'm each is a 64 by 1 vector, but I'm visualizing them 8 by 8 blocks. Here I have completely flat. Now this is a slowly varying sinusoid in one direction, a little bit fast, a little bit fast, and this is a very fast varying sinusoid in one direction. This is the same thing in the other direction, and then these are their combinations. So this one is changing fast in both directions, for example. Okay, this one is changing very fast in one direction and a bit slower in the other direction, and so on. So these are the basis vectors used in JPEG compression. When we transmit the image, we transmit only the coefficients, not the basis vectors, because we know them. So there is an encoder, there is a decoder. The encoder knows the basis, the decoder knows the basis, and so we transmit only the coefficients, and that's what gives you compression. In fact, all your compression algorithms, a lot of your compression algorithms are actually like MPEG, for example, does a similar strategy on video. Even this type of conversion is available in H.264 and in a lot of codecs. It's a very fundamental step in compression. So I'm going to take a few more minutes. So I want to finish this topic, so you just have to bear with me. So the question is, which basis should we choose? DCT is just a rotation of the original identity basis, and I can rotate in a lot of number of ways. So I could have chosen some other basis. Why choose DCT? Or is there some other basis that I should choose? Okay, so DCT basis is an orthonormal basis, which is just a rotation of the standard identity basis, right? So why not choose some other orthonormal basis? Why not choose maybe any other rotation than DCT? DCT is one particular rotation. Okay, so in fact the question is, how do I answer this question? Is there some other standard basis? Is there some other rotation of the standard basis which is better? You understand the question? So then the question becomes, how do I define better? How will I say basis A is better than basis B? Yeah. Sorry? I could check compactness. Yeah, that's a good point. Okay. So let me just, there are these two slides where I've built this argument, so I just want you to follow those. So this leads us to the question, what is the criteria for changing a basis? Which basis is better? Okay. Now recall this type of data, which lies in some subspace. So I want that basis to span that subspace. Okay. Well, if that's the case, whatever is the subspace my data is spanning, if I choose a basis to span that subspace well, it will be more compact. Okay. So generally speaking, basis which represents data more compactly is better, and that means basis which is aligned with data orientations is better. Why? Because if my basis is aligned with data orientations, I showed you when we discussed this KLT part, if I have bases which are aligned with my data orientations, then the covariance matrix comes out to be diagonal only. All the off diagonal terms become 0. Okay, and so if my covariance matrix comes out to be diagonal, and in some dimensions like this vertical one I have 0 variance, I can just drop those. So choosing a basis that decorrelates my covariance matrix, 0 mean compensated covariance matrix, is actually a good idea. That will give you better compression. Do you follow that argument? Why did covariance come in? Because bases with okay, so let me say this in a different way. It turns out we have found, let's say just by chance or luck or experimentation, that DCT represents natural images very well. This is not a natural image. This is a random image. DCT will not represent this very well. Okay, so but natural images DCT represents very well, because natural images are not random. What they do, what that means is that natural images span a compact subspace out of all the possible vectors that I could have created of this size, this image size. Well, like one of them is just random, but this random image is surely not a natural image. This is not an image you would ever shoot from your camera, unless you were like picturing QR codes or something like that, right? I mean, naturally, if you were on a hiking trip, your image would never turn out to be like this. Okay, so that tells me that natural images, the sort of images that you would shoot on a hiking trip, actually lie in a compact subspace of the possible vectors that I could have created out of that size. Now, if that is true, what's the basis that I want? I want a basis which will span that subspace more compactly. Okay, so is there an optimal basis? Well, that really depends on the data set, really. I mean, what type of subspace does my data lie in? Of all the possible images that I can create, what subspace do they span? So for a given data set, actually we can find the best orthonormal basis, the best orthogonal basis for that, in the sense that no other basis will represent that data more compactly. Okay, I'm trying to motivate an optimal basis now. Okay, I'm saying this is possible, but why is this possible? What should be the characteristic of that optimal basis? Now, if you look at this figure, let me make a statement and see if that makes sense. I'm saying the optimal basis should align along the direction of the data spread. If the data is on a plane, the optimal basis should align on that plane. Then I will get compaction. Otherwise, I won't. If let's say my space is 10-dimensional, and there is a 5-dimensional subspace at an angle going like this in that 10-dimensional space, I want a basis which aligns with this 5-dimensional space. Now notice that the original 3-dimensional vectors, the original identity vectors here, also span this space, but they don't just span this space. They span something more, and that's why I don't get any compression. Each point is a 3-vector, but when I write them as 3 vectors, I don't exploit this fact that I want to, if I had a basis spanning this space only, then that would give me more compression. That's the key idea. Okay, so this statement is critical then. I've reached this conclusion that the optimal basis should align along the directions of data spread. And how do you find data spread? Variance. Data spread is variance, right? So after alignment, after I align this to after I do a change of basis, my covariance matrix should become diagonal. Because if the covariance matrix is diagonal, remember this, oops. No, my pen is, what happened? What did I do last time to be able to do this? All right, forget it. I think I'll write this on the board. Remember this figure? If I have data spread out like this, then the covariance matrix is not diagonal. Okay? But if I do a rotation of axis so that this data spreads like this, then the covariance matrix is diagonal. And why is that? Because now if I tell you the x value, you can tell me nothing about the y value. But in this case, if I tell you the x value, you can tell me something about the y value. That the y value is high if the x value is high. Okay? So the off-diagonal terms become 0 if I align my axis along the basis. So it's actually, I'm using the same concept, but now in reverse. There we said, okay, if you give me some data, I can decorrelate it, right? Now I'm saying I will use the basis that align along the axis because that will decorrelate it, and that actually is the best representation because that basis is aligned along my data directions. Okay? So how do I do that? Well, the same way. If I rotate the data by r, the covariance matrix, now I used a different symbol here just for nothing really, but the covariance matrix L, which is the mean, the covariance matrix of the mean compensated data, so that the data has 0 mean. So that rotates by r, L, r transpose, right? We have seen this before when we were doing KLT. So therefore, if I wanted to diagonalize the covariance matrix, I have to choose R as phi transpose, where phi is the matrix of eigenvectors of L. If I choose that, exactly the same thing as we did before, that's the basis which will diagonalize my covariance, and it will be naturally a good representation of my data. Okay? So how do I compute the optimal basis? Well, here's a procedure. You give me a lot of images, I1, I2, IN. These are a lot of images. This is my data set. I want to compress all of these images. Okay? So what I'm going to do is I'll compute the mean of them, and then I'll subtract, oh, so this should be L really, so let L be a matrix which contains each image as a column vector, and then I subtract the mean from them and then compute the variance, right? So this is actually covariance of mean subtracted data. It's really like A minus mu I transpose. I've written it like this. Okay? So that's the covariance matrix, which means I subtract the mean of every image from it, so it's become 0 means, and then I just compute A transpose of that. Okay? And then I find the eigenvectors of L, I make them phi, and then I project the data onto phi, which means I really rotate by phi transpose. Okay, that's what you do. I mean, the same thing as we did in KLT, the same thing as we did in DCT and so on. And then this will be the most compact representation of my data because my axis has now become aligned with my data. Okay, so I can just throw out all those axes now which don't have any spread of data, which have zero variance on them, and only use those which have a significant variance, which means significant eigenvalues. Typically, a lot of eigenvalues after I do this will become close to zero, and I can just discard those vectors. And then this is called the Carnot-Loewe transform or principal component analysis. It's very famous. You might have heard this name, PCA, somewhere before. Now, I was talking about DCT and people use DCT. DCT is not like this. This is a different transform. This transform is computed from data. DCT basis I already knew. Okay, but it turns out that for natural images, DCT approximate PCA. If you take what do I mean by that? If you take a very large collection of natural images, okay, and then from that you computed your basis, you computed your principal component analysis basis. I mean these Carnot-Loewe transform basis. It turns out that they look awfully like the DCT basis. So DCT is a good approximation to KLT, except KLT you need to estimate from data. DCT you know mathematically, you know it from before, you know it in its, you know the form of DCT, so you don't have to compute it from your data. Okay, and that's the reason why JPEG is so popular, because they hit on this idea that let's use DCT. Theoretically speaking, it turns out that DCT is an approximation of this optimal basis. Why is that? We are not going into that. There's actually a seminal paper written in 1976 that described this link theoretically. There's a good theoretical reason for DCT to approximate PCA. They showed that if data is of certain type, to be specific for those who are interested, if your images can be described as a random vector generated out of a Markov 1 random process. For those who have taken which course? Probability course, random variables course, the one Ehsan Kazi teaches, applied probability. Yeah. So what's a Markov 1 random process? Yes. Yeah, you've taken that in the course. Yeah. No. Have you talked about Markov random processes there? No, but in applied probability they do, right? Who has taken applied probability? Only one person in the whole class? How many people are graduate students here of CS? Oh, आप हाथ क्यों नहीं गड़ा मुकर गए? Have you taken applied probability? Yeah. Okay. So did we talk about random Markov? I mean, the rest shouldn't get scared. There is. All I'm saying is I don't want to go into this because it's beyond the treatment of the course. But I'm saying is there is a good theoretical reason also that if the data is of a certain type, then DCT can be mathematically shown to. I mean, you compute PCA and it turns out to be DCT for certain type of data. For those who are interested, that data is Markov 1 random process with high correlation. I mean, you can just say that it happens. So DCT is a good approximation to KLT for natural images, and it's known. KLT is not known unless you specify my data. I mean, by KLT here, I mean Carnot-Loewe transform and not the Kanade-Lucas-Tomasi corner detector. Okay? This also is KLT, but very different people and very different transform. Okay, I will conclude this tomorrow, inshallah, by showing you why this change of basis can be used as a feature. Okay, and how can I build classifiers on top of it? And from there on, we will talk about classifiers in a more formal way. All right? Okay, thank you.
So how many lectures are you running after this?